Hello once again. You are welcome to our SHS 3 Core Mathematics lesson brought to you by the Center for National Distance Learning and Open Schooling. I am Lucy Asari Nelson. The topic for my presentation today is Introductory Calculus. That sounds new, isn't it? Introductory calculus is one new topic that has been added to the examination syllabus. So for you to get an A in your core mathematics, you have to know something about it. In this lesson, we shall discuss differentiation of algebraic functions. By the end of this lesson, you should be able to A. Explain the concept of differentiation or the derived function. B. You should be able to find the standard derivatives of some basic functions. And C. You should be able to find the relationship between gradients of a curve at a point and the differential coefficient of the equation of the curve at that point. Calculus is a branch of mathematics which focuses on limits, functions, derivatives, integrals, and infinite series. Calculus is the study of change in the same way as geometry is the study of shapes and algebra is the study of operations and their applications in solving questions. Calculus has widespread uses in science, economics, and engineering, and can solve many problems for which algebra alone cannot. Calculus is divided into two main categories. One, differential calculus, which we normally call differentiation. And two, integral calculus, which we would call integration. Let's look at differential calculus. Differential calculus cuts something into small pieces to find out how it changes. On the other hand, integral calculus joins or integrates the small pieces together to find out how many they were. Now let us consider differentiation. You may recall that to find the gradient of a straight line, we divide the change in y by change in x in a certain range of values. That is, we are very familiar with the ratio change in y divided by change in x, which we normally write as y2 minus y1 divided by x2 minus x1. The gradient of any straight line is uniform and is a constant value. It's uniform, meaning it is the same wherever you take it, and it is a constant value. However, when it comes to a curve, the gradient keeps changing from point to point, from one point to another. So we have to draw tangents at all those points and then find the gradient of the individual points, as you can see on the diagram. On this diagram, the lines you see touching the points, touching the curve, are the tangents at the points you see them. So we have the tangent drawn. Remember in SHS 2, we studied the topic geometry, and we saw what a tangent is. It is this same concept that we are carrying here. Remember, the part of a curve looks like a circle. So any line that is drawn to touch a curve at any point is a tangent. If we stick to this formula, we will have to draw hundreds, if not thousands, of tangents to find the gradient of various points on a curve. The good news is that there is a method that comes in to rescue us. And that method is called differentiation. So differentiation is the process of finding the gradient of a slope of a function. It provides us with the method that finds the rate of change of graphs. The value obtained is called the differential coefficient. And that is written as dy dx, or f prime of x. That is what we call the gradient. Differentiating dy dx with respect to x. And what you see in the brackets, WRT, only means with respect to. I want you to note that a derivative is basically the slope of a curve at a single point. Now let us look at some basic differentiation rules. Some differentiation rules are easy to remember and use. These include the power rule, the constant rule, the constant multiple rule, the sum and difference rules. I want us to look at the power rule. To differentiate any function, y is equal to ax exponent n, we use dy dx is equal to a times n times x exponent n minus 1, where dy dx is the derivative. A is a coefficient of x, and n is any real number. So to find the gradient at any point, we only have to substitute the x value for dy dx, and that will give us the gradient. I want us to take an example. If f of x is equal to x cubed, then to find the derivative, bring the exponent 3 in front of x. That is what we are calling a. And then reduce the exponents by 1. So here, a is equal to 1, n is equal to 3. So dy dx is equal to 1, which is a, times 3, which is n. Then we bring our x, and then the exponents minus 1. So 3 minus 1, just as we gave in the power rule. When we simplify this, we will have dy dx is equal to 3x squared. Dy dx is the same as f prime of x. Hence, f prime of x is equal to 3x squared. That is the power rule. The power rule works for any power, positive, negative, or even fractions. Let's take another example. If f of x is equal to 2x exponent 10, then f prime of x will be equal to 2, which is a, multiplied by 10, which is n. Then we bring our x, and then n minus 1. So 10 minus 1. So f prime of x, when we simplify, will give us 20x exponent 9. This 20 is 2 times 10. When you want the derivative of a sum and difference of terms, we simply take the derivative of each term separately using the power rule. So we say that differentiation of algebraic expressions is done term by term. Let's take an example. Find dy dx if y is equal to 2x cubed plus 5x squared plus 4x. In this expression, 2x cubed represents the first term, 5x squared the second term, and 4x is the third term. So we are just going to use the power rule on each of the terms, and that gives us our differential. So as discussed earlier on, if y is equal to ax exponent n, then dy dx is equal to an x exponent n minus 1. In the given function, which is y is equal to 2x cubed plus 5x squared plus 4x, dy dx will become 3 times 2x squared plus 2 times 5x exponent 1 plus 1 times 4x exponent 0. That is when you use the power rule. When we simplify, we will multiply the exponents by the coefficients, and then we simplify. That is exactly what we have done. So dy dx, when we simplify, will give us 6x squared plus 10x plus 4 as the answer. Now let's take another example. Example 4. If y is equal to x cubed minus 2x squared plus x, find dy dx. Using the power rule, dy dx is equal to nx n minus 1, or anx exponent n minus 1. So when we simplify, we'll have dy dx is equal to 3x squared minus 4x plus 1. I hope you are getting along. Good. Now I want us to look at how we can differentiate a constant term. So let's take example 5. Differentiate f of x is equal to 5. Let's see the solution. In differentiation, it is important to recall your ideas on indices. So from indices, we are aware that x exponent 0 is equal to 1. Any number exponent 0 is 1. So we can write f of x is equal to 5 as f of x is equal to 5 times x exponent 0. Therefore, using the power rule as discussed earlier, we can differentiate the constant 5. So we have the power rule dy dx is equal to a multiplied by n multiplied by x exponent n minus 1, where a is equal to 5 in this case, n is equal to 0. So dy dx is equal to 5 multiplied by 0 multiplied by x exponent 0 minus 1. But 0 multiplied by any number is simply 0. And so dy dx becomes 0. I hope that is clear. Good. That is for any constant number represented maybe by c. If f of x is equal to c, then f prime of x is equal to 0, or dy dx is equal to 0. We can also write d dx of c is equal to 0. Good. I want us to take example 6. If y is equal to x cubed plus 2x squared plus 1, find dy dx. Let's take the solution. Using dy dx is equal to an x exponent n minus 1 and differentiating term by term, we'll have dy dx is equal to 3x squared plus 4x plus 0. Simplifying that will give us dy dx is equal to 3x squared plus 4x. Simple, isn't it? Good. Example 7. Differentiate with respect to x, y is equal to, in one bracket, x plus 1, multiplying another bracket, x minus 4. Let's take the solution. There are some other methods of differentiation we can use, but let us expand and simplify first. So when we expand this, we are going to have y is equal to x squared minus 4x plus x minus 4. And simplifying that will give us y is equal to x squared minus 3x minus 4. Having done this does not mean you have differentiated yet. You have only simplified the original. So we are now going to differentiate. So dy dx becomes 2x minus 3 minus 0. And we simplify that to get dy dx is equal to 2x minus 3. It's simple, isn't it? Good. Take another example. If y is equal to 1/3 x cubed minus x squared minus 24x plus 2, I want us to find dy dx. Let's take the solution. Again, there are 4 terms in this. We'll differentiate them term by term using the power rule. So we have dy dx is equal to x squared plus 2x minus 24 plus 0. We'll simplify that to get dy dx is equal to x squared plus 2x minus 24. Well, we'll take another example. In this case, there is a negative exponent. If f of x is equal to x exponent negative 2, let's find dy dx. Solution. Using the power rule, it becomes simple. Just use the exponent negative 2 to multiply the coefficient of x and then reduce the exponent by 1. And so dy dx becomes negative 2x exponent negative 3. Simple. Good. Example 10. If f of x is equal to the cube root of x squared, find dy dx. Let's take the solution. Again, we will use the ideas from indices and then rewrite f of x as f of x is equal to x exponent 2/3 and use the power rule to differentiate. So dy dx becomes 2/3 x exponent 2/3 minus 1. And when we simplify that, we will have dy dx is equal to 2/3 x negative 1/3. Great. Therefore, dy dx is equal to 2/3 x exponent negative 1/3. Remember that dy dx means differentiating y with respect to x. It means that the p dt will mean differentiating p with respect to t. Once we have this, the power rule will still hold, and we are going to differentiate term by term. So we have been given p is equal to 3t squared minus 2t plus 1. And the p dt will give us 6t minus 2. Simple, isn't it? we can use any variable depending on which one is the independent variable and which one is the dependent variable. We can find the derivative or the differential. Let's take another example. F of x is equal to 3x cubed minus 12x squared plus 5. If f prime of x is equal to negative 3, find the value of x. Let's take the solution. The y dx, you know, is also f prime of x. So f prime of x is equal to 9x squared minus 24x plus 0. Now, f prime of x, when simplified, will give us 9x squared minus 24x. But we were told f prime of x is equal to negative 3. So in place of f prime of x, we would put negative 3. That will give us 9x squared minus 24x is equal to negative 3. But then there's a common factor here, which is 3. So we will use 3 to divide through. And that will give us 3x squared minus 8x is equal to negative 1. Then we transpose. We want to bring all to one side and equate to 0. So we'll have 3x squared minus 8x plus 1 is equal to 0. Now, this equation we have is a quadratic equation. And remember, quadratic equations must always be written in the standard form if we want to use the quadratic formula to solve them. So we want to use the quadratic formula to solve this. Remember the quadratic formula. X is equal to negative b plus or minus the square root of b squared minus 4ac all divided by 2a. In our quadratic equation that we have, a is equal to 3, b is equal to negative 8, and c is equal to 1. So we want to substitute these values into our quadratic formula. So x is equal to negative into bracket negative 8 plus or minus the square root of negative 8 squared minus 4 times 3 times 1, all divided by 2 times 3. When we simplify that, we have x is equal to 8 plus or minus the square root of 64 minus 12, all divided by 6. Now remember, before you square negative 8, make sure it's in brackets, because some calculators will only accept that when it is in brackets. Now, the other part will give us the square root of 52. So we have x is equal to 8 plus or minus the square root of 52 divided by 6. So you take your calculators, take the square root of 52, and then we proceed. So x is equal to 8 plus or minus 7.2111 divided by 6. At this point, we can separate them. So we have two answers. In the quadratic expression or the quadratic formula, the two answers gives us the negative plus or minus situation. So x is equal to 8 plus 7.2111 divided by 6 will be for one of our answers. When we simplify that, it will give us 2.5352. The second value for x will be given by x is equal to 8 minus 7.2111 divided by 6. And that will give us x is equal to 0.1315. Good. I now want us to look at some applications of differentiation. The gradient function. If y or f is a function of x, then the first derivative, dy dx, or f prime of x, is called the gradient function. So any time you differentiate, you get dy dx, whatever you obtain is the gradient function. The gradient of a curve at any point, say P, x1, y1, is obtained by substituting the value of x1 into the expression for dy dx. It means that if you want the gradient at a point on a curve, just differentiate the function for the curve and then substitute the x value of the point into your differential, and that gives you the gradient. This is the same as the gradient of the tangent at the point P, x1, y1. Let us take some examples. Find the gradient of the tangent to the curve y is equal to x cubed minus 2x plus 1 at the point -1, 2. Let's take the solution. We have been given y is equal to x squared minus 2x plus 1. dy dx will give us 3x squared minus 2 plus 0. That is when we differentiate using the power rule, term by term. When we simplify this, we will have dy dx is equal to 3x squared minus 2. Now, at the point -1, 2, dy dx will be equal to 3 into bracket -1 squared minus 2. That is, just substitute the x value, which is -1, in place of x. When we simplify that, it will give us 3 minus 2, which is 1. So dy dx is equal to 1. Therefore, the gradient of the tangent is 1 at that point, at the point -1, 2. Good. Let's take another example. F such that x maps to x squared plus 3 all squared is defined on the set R of real numbers. Find the gradient of f of x at x is equal to 2. So f of x is equal to x squared plus 3 in one bracket and x squared plus 3 in another bracket. We would expand that to get x exponent 4 plus 6x squared plus 9 for f of x. Now we want to differentiate. So f prime of x becomes 4x cubed plus 12x plus 0. F prime of x, when simplified, becomes 4x cubed plus 12x. 4x cubed plus 12x. Now, at the point where x is equal to 2, we simply substitute 2 in place of x in f prime of x. That means f prime of x is equal to 4 times 2 cubed plus 12 times 2. And so that will give us f prime of x is equal to 4 times 8 plus 24. And that will give us 24 plus 24, which is 48. So f prime of x is equal to 48. Therefore, the gradient of the tangent of f of x at x is equal to 2 is 48.
Action.
Well, my dear students, we have come to the end of today's lesson. I want you to join me for another lesson where we would look at calculus, this time the rate of change. Until then, it's goodbye.